Hi, we are Team MIST Mongol Barota from Bangladesh, introducing our all-new rover CELESTE-1. Welcome to the System Acceptance Review for University Rover Challenge 2026. This year, CELESTE-1 features a new differential bar with a modular stainless steel chassis. It has a larger detachable design for easier maintenance, weighing 39 kg with the arm and under 45 kg with the science module. The four-wheel rocker bogie design ensures stability on rocky, uneven and sandy terrain. The leg assembly adopts a trapezoidal configuration fabricated from aluminum 6061 alloy, achieving a 50.52% weight reduction through topology optimization while maintaining structural integrity. DC motors from the previous year have been replaced with BLDC motors, improving torque delivery and overall efficiency, allowing it to climb 45-degree inclines and traverse 40-centimeter obstacles. Airless TPU wheels with a honeycomb internal structure replace the previous trapezoidal geometry, achieving a 23.32% weight reduction while improving vibration damping, traction, and terrain adaptability. All machine components have been fabricated in our institute's lab. The 5 degrees of freedom rover arm is built from parallel links of carbon fiber with optimized strength-to-weight ratio. The sprocket gear mechanism of the base joint has been replaced with a stepper motor coupled with a bevel gearbox. The gripper pitch and roll axes are independently powered by BLDC motors, improving precision while keeping the system lightweight. The stepper-driven gripper claw with a belt pulley mechanism can lift and transport payloads up to 7 kg and reach 1.5 meters. It has a fixed parallel jaw with an actuated lead screw, providing precise parallel movement for 80mm grasping. The robotic arm performs targeted operations on instrument panels, including actuating buttons, toggling switches, and executing USB-C insertion. It can operate a 4-position spring-return joystick, open and close latch doors, and sliding drawers. From within these compartments, the end effector retrieves standard hand tools. It can adjust its grip to pick up a test tube and place it directly into a designated holder. The control architecture now incorporates autonomous typing routines. Improved inverse kinematics guides the positioning and motion control. We developed a custom battery pack composed of LiPo cells, delivering a total output of 48 volts and 22 ampere hours. The electrical dashboard has been redesigned to display all critical power metrics. Additionally, this year, we introduced a dedicated power distribution board, separated from the main control unit. This upgrade ensures stable and sufficient current delivery to all subsystems. We upgraded to the NVIDIA Jetson Orin with 2 Raspberry Pis to tackle the bandwidth overloading issue. Upgrading previous architecture, a unified all-in-one hot-swappable PCB powered by TNZ 4.1 microcontroller. CAN-FD protocol is used to ensure reliable and synchronized control of all BLDC motors. A clearly visible kill switch is incorporated to allow immediate power shutdown whenever necessary. For this year, we have finalized the 5 GHz and 900 MHz bands as our core communication frequencies, operating under the IEEE 802.11 wireless communication standard. The 5 GHz link pairs a 120-degree base station sector antenna with an onboard omnidirectional antenna, allowing high-resolution video feedback from our 4 separate USB cameras. Meanwhile, the 900 MHz link utilizes a directional base station Yagi antenna, communicating with a dual antenna setup on the rover to ensure control commands and a dedicated long-range video feed for mission-critical situations. Instead of relying on fixed coverage angles of the directional antennas, we engineered a custom auto-rotational mount that keeps the base station antennas aimed directly at the rover. Building on last year's foundation, we have moved away from the mixed ROS1 bridge system to a fully distributed ROS2 architecture. For localization, we have evolved beyond the standard RTK setup. This year, we are integrating VSLAM using a stereo depth camera. Upon fusion with GNSS data, we can achieve a drift rate of less than 5 cm, allowing precise navigation. Through our dashboard, operators can set waypoints, which our new waypoint manager transforms into local goals. Our custom ROS2 pipeline now utilizes real-time 3D point cloud for dynamic obstacle avoidance, moving away from previous LiDAR-based laser scan. Upon reaching a coordinate, we use Pentagon search pattern to find ARUCO tags or objects. Our ARUCO package detects tags at 12 meters, and a physical polarizer added to the camera lens based on previous field tests filter out harsh glare. Once a tag is detected, our upgraded control algorithm now allows the rover to robustly follow the ARUCO tag even across sloped or uneven terrain, confirmed by a green LED. As with our previous iteration, our custom YOLO model identifies mallets and bottles, guiding the rover to within 2 meters of the target. The entire science module is now fully modular, allowing quicker attachment, maintenance, and disassembly during operations. Compared to last year, we replaced the scooping mechanism with a rotary impact auger drill, allowing direct penetration and collection of subsurface soil. This improves sampling efficiency while reducing handling time and exposure to environmental factors. Drill cuttings are guided through an aluminum casing, where the upper contaminated 10 centimeters of soil are discarded. The cache container is then sealed to collect further soil sample of up to 8 grams. The collected soil is guided into an 8-beaker carousel for chemical analysis. Test chemicals are stored in sealed custom containers to prevent spillage, while peristaltic pumps provide controlled reagent delivery. The system performs 4 complementary biosignature tests: the burette test for proteins, iodine testing for polysaccharides, a faster heat-free replacement test for previously used Benedict's test providing faster results, and a newly added lipid detection test. Finally, a gas sensor measures ammonia releasing from freshly collected soil. Instead of binary conclusion, this year our system applies a probabilistic interpretation framework, classifying results into extant life, extinct life, probable alternative biochemistry, or no detectable life. For geological investigation, the microscope captures detailed images of collected rock samples at 1600 times magnification. A trained rock identification model assists in rock type classification, which was expanded with 1300 additional rock samples, improving identification accuracy to 93.2%. The NPK sensor provides subsurface soil temperature, nitrogen, phosphorus, and potassium data. With the vision of extending our mission of space exploration beyond our lab, we have conducted in-depth workshops, hands-on robotics training, and seminars. We look forward to meeting you in Utah this year. On behalf of Team MIST Mongol Barota, thank you for your time and best wishes to all the teams.